Okay, so it's a pleasure to have with us Jaikrishnan Janardhanan from IIT Madras. He will talk about holomorphic symmetric product of a Riemann surface.
So thank you for this invitation to come and give a colloquium here. So I will be talking about a symmetric product of a Riemann surface and certain results on these complex manifolds. So before I begin, let me just set up the notation. So suppose D subset of Cn is a domain F from D to C is said to be holomorphic, if it admits a local power series expansion at each point. Of D. A holomorphic mapping, suppose I am given another domain omega in Cm, a holomorphic mapping is just a map from D to omega such that each coordinate is a holomorphic function in this sense. So I will be considering complex manifolds. A complex manifold is nothing but a two-dimensional real manifold, sorry, 2n dimensional, it's a 2n dimensional real manifold with the transition functions being holomorphic, with holomorphic transition functions. So throughout this talk, all complex manifolds I consider will be connected. So the space of holomorphic mappings from a complex manifold X to a complex manifold Y would be denoted OXY. So that's the preliminaries. So let's get on with the talk. So let me first explain what the symmetric product is. So when you take the Cartesian product, it comes with a natural ordering. There is a first coordinate, there is a second coordinate, there is a third coordinate. In some scenarios, it might be better to forget about this ordering and consider the symmetric product. One instance is when you are considering the roots of a one variable polynomial over C. The roots don't come with any specific ordering, and we intuitively see that the roots of a one variable complex polynomial will vary continuously with respect to the coefficients. This is one way of making that notion precise. So what you do is you consider any topological space and denote the orbit under the Sn action by angular bracket x1 to xn. You consider you quotient out xn by this action, call that the symmetric product. So you equip sim n x with the quotient topology. Okay. So and the quotient map is called pi sim. It happens that when you are considering domains in Cn, or rather if you consider the symmetric product of the complex plane, you can describe this mapping in a different way. So let sigma j denote the elementary symmetric polynomials of degree j in n determinates and indeterminates, and look at this map pi superscript n. This is called the symmetrization map. You will notice that this symmetrization map essentially makes the same identifications as the map pi sim. So this sim n x, so what I want to say is you get a mapping, you get a mapping from sim n c to this second map. So look at this map, pi n from Cn to Cn, you get a map from sim n c to Cn. This map is obviously going to be continuous, and it's going to be bijective, an application of Rouché's theorem will tell you that the inverse of this map is also continuous. So the symmetric product here is in fact biholomorphic to Cn itself. So this is something that happens only in dimension 1. One object that we define is the symmetrized polydisk, which is just the image of the usual polydisk, the Cartesian n-fold Cartesian product of the unit disk. This we call the symmetrized polydisk. So the first few next 20 minutes I will spend motivating why the study of the symmetrized polydisk is intrinsically interesting from the perspective of complex analysis. Now because dimension 1 is special, if you take a Riemann surface and consider the symmetric product of the Riemann surface, you can equip a natural complex manifold structure on it where the local charts will be biholomorphic to the symmetrized polydisk. This thing is special, it happens only in dimension 1. In higher dimensions, in general, when you take the symmetric product, you will end up with what is known as an analytic space. That space will be locally biholomorphic to a variety and not a manifold. So now I am going to motivate why the symmetric product is very important from the perspective of complex analysis. Yes, can you repeat that? Difference between? So pi sim is this this map, the mapping for this action. Something not visible? Pi n is just this collection of elementary symmetric polynomials.
So you are thinking from NC to C, I mean,
Yeah, this
what is the domain of this pi n?
this domain of pi n is Cn, but the map descends to sim n also, simply because it respects the identifications made by sim n.
So what is the domain?
The domain is Cn only. The domain of pi n is Cn, but it also descends. You can the domain of pi n is just Cn, not the symmetric product. So
Pi n is the image of Cn other pi n.
yes, that's all. So let me spend some time motivating why the symmetrized polydisk is a natural object to study from the perspective of complex analysis. For that I need to introduce some notions, invariant metrics. So to transfer problems in complex analysis to geometry, one typical tool that we use is to equip a complex manifold with a pseudo distance or a distance such that holomorphic mappings between manifolds become contractions. So one standard way to do this is to use the Mobius pseudo distance. Given a complex manifold X and 2 points Z and W in X, you look at the collection of all holomorphic mappings from X to the unit disk such that f of Z is 0. Then you take the supremum over mod f of W. This object is called the Mobius pseudo distance. Instead of taking mod f of W, if you had taken the Poincare distance rho d of f of W 0, then what you get is the object known as the Carathéory pseudo distance. So the Mobius pseudo distance we denote by mx and the Carathéory pseudo distance we denote by cx. So you can check very easily that for the unit disk, as expected, the Mobius pseudo distance is nothing but mod z minus w by 1 minus wz bar, and in general tan hyperbolic of cx will be mx. Now of course I claim that they are pseudo distances, and it is not at all hard to show. Both of them will be pseudo distances, and right at the surface you see that there is a problem because there are no non-constant holomorphic functions on a compact complex manifold. Both cx and mx will be identically 0.
Actually, I'm having a problem because before it thinks it's going away.
Okay, sorry. Pseudo distance is just the usual notion of metric, except it's possible that dxy is 0 even when x is not equal to y. A pseudo distance satisfies all the conditions in a distance, a metric, except that it's possible that dxy is 0 even if x is not equal to y.
So, for example, you want to say that M of ZW is same as M of W?
Yes, it is true. That's because the automorphism group of the unit disk is transitive. I can just interchange the image points. X is the disk itself. The Mobius pseudo distance will be mod z minus w by 1 minus wz bar.
Obviously, this is invariant and
Right, right. Fine. Okay. Shall I switch over the slide? Okay. So, in fact, it is not hard to show that these are in fact pseudo distances. And there is a problem already, because whenever x is compact, both pseudo distances will be identically 0. And just from the very definition, it follows that both the when you equip the Mobius pseudo distance or the Cartiotti pseudo distance on both x and y, it will turn out that holomorphic mappings are distance decreasing contractions. In particular, if you consider a biholomorphism from x to y, they will be isometries when you put the Mobius or the Cartiotti pseudo distances on both x and y. As I mentioned, in most cases, especially for compact, it's identically 0. We want to specialize to those manifolds for which.
So, I have a very basic question.
Right.
Does it give the same topology?
No, I will mention that in a while. It does not give the same topology. So, what we do now is we define a manifold to be complex manifold to be C hyperbolic if the Cartiotti pseudo distance is an honest distance. If the metric space XCX is a complete metric space, then we say that X is complete hyperbolic. Okay. So, the unit disk is a complete Cartiotti hyperbolic, whereas the complex plane C minus 0 1, in fact C minus any finite set of points, and compact complex manifolds, none of them are Cartiotti hyperbolic. So, suppose you have a holomorphic mapping from C minus 0 1 to the unit disk, then because it is bounded, 0 and 1 have to be removable singularities. So, this mapping will extend to be holomorphic on C and therefore has to be constant. So, because there are no non-constant holomorphic mappings there, both pseudo distances will be identically 0. Okay. So, we say it's Cartiotti hyperbolic if the Cartiotti pseudo distance is a distance. Now, as I mentioned, there are many problems for this Cartiotti pseudo distance. First is that it's often identically just 0. The second problem is the question, does the topology generated by this metric, suppose you assume that it's Cartiotti hyperbolic, does it mean that the topology generated agrees with the original manifold topology? And it's not. It does not agree. So, we wanted to study, not we as in the community wanted to study, is it possible to put some other pseudo distance on the complex manifold which does not have these deficiencies. So, the general idea is on any complex manifold you equip it with the pseudo distance such that for the unit disk you always put the Poincare distance, and under this system of pseudo distances holomorphic mappings between complex manifolds become distance decreasing, or in other words contractions. So, that is the general aim, and such a system is called a contractible family of invariant metrics. So, now observe that we define the Cartiotti pseudo distance or the Mobius pseudo distance by considering holomorphic mappings from the complex manifold into the unit disk. Say you have equipped the complex manifold X with a distance rho x such that holomorphic mappings from X to D become distance decreasing. That means you put the Poincare distance on D, you put this rho x on X, and holomorphic mappings will become distance decreasing. That is just saying that rho D f of z f of w will be less than or equal to rho x z w for all z w in X, right. Now what you do is on the LHS you take supremum over all possible holomorphic mappings. Then it's clear that what you get on the left hand side is nothing but the definition of the Cartiotti pseudo distance, right. So what this says is that the Cartiotti pseudo distance is in some sense the smallest possible distance you can put on a complex manifold such that the holomorphic mappings become contractions, and that is why it is turning out to be identically 0 in many cases. Now we want to consider another family of useful pseudo distances introduced by Kobayashi, which will be in some sense the dual of the Cartiotti pseudo distance. It will be the largest possible pseudo distance. So let me just briefly give the definition of the Kobayashi pseudo distance. You have a complex manifold X. You have a complex manifold X. So the idea is, since we are taking the dual, the natural thing to consider would be mappings from the unit disk into X. So take 2 points Z and W in this complex manifold and look at holomorphic mappings from the disk to the complex manifold. As I mentioned, all complex manifolds I will consider only connected ones. Now there is no reason to believe that there will be a single holomorphic function from the disk to the complex manifold X such that the image swallows up both Z and W. There is no guarantee that that will happen. So what you do is you consider a chain of points P0, P1 to Pk, the first one P0 being Z and the last one Pk being W, such that successive points are in the image of a holomorphic function from the unit disk to the complex manifold X. Then let's say the point x1, y1 in the unit disk gets mapped by f1 such that f1 of xn is z and f1 of y1 is p1, and so on and so forth. f2 will be a mapping such that f2 of x2 would be p1 and f2 of y2 would be p2, so on and so forth. Then you look at this collection, this sum, rho d of x1 y1 plus rho d of x2 y2 plus rho d of xn yn. And now you infimize over all possible chains and all possible holomorphic mappings. Rho d is the Poincare pseudo distance. I mean distance, it's actually a distance on the disk. Rho d is the Poincare distance on the unit disk. And you infimize over all possible chains and all possible holomorphic functions. And the object you get is the Kobayashi pseudo distance. Again, it's straightforward to check that this is in fact a pseudo distance. And in some sense it's the dual of the Kerr theory. One can show that this is the largest possible pseudo distance you can put, under which holomorphic mappings become contractions. And just as we did for the Cartiotti pseudo distance, that means that suppose you have a holomorphic mapping from x to y, then ky of f of x, f of y would be less than or equal to, let me just write that, f from x to y, ky of f of x, f of y would be less than or equal to kx of xy. So in particular, biholomorphism will be isometries once you put this this distance on both the domain and the target. So exactly as we did for the Cartiotti pseudo distance, one can define the notion of k hyperbolicity. Yes, well, it's a nice neat exercise to check for the complex plane or C2 or C3 or Cn, the Kobayashi pseudo distance would be identically 0. It's not, yes, you can enlarge. So this is not perfect, but it is better than the Cartiotti pseudo distance. I will momentarily explain why it is better. So you can make similar definitions of K hyperbolicity. That means if the Kobayashi pseudo distance is a distance, then we say the manifold is K hyperbolic. Similarly, you can define complete K hyperbolic if the metric space is complete. Now, unlike the Kobayashi pseudo distance, unlike the Cartesian pseudo distance, whenever the manifold is hyperbolic, the topology generated by the Kobayashi distance is exactly the manifold topology. So, in some sense it respects the original topological structure, so that is nice. And not only that, there is a convenient way of checking whether a manifold is Kobayashi hyperbolic or complete Kobayashi hyperbolic. If the manifold X is covered by the manifold X prime, then X is complete Kobayashi hyperbolic if and only if X is. So, this is very useful because in particular it will imply that in dimension 1 being complete Kobayashi hyperbolic is equivalent to being covered by the unit disk. So, by the uniformization theorem there are only three possibilities: either the Riemann surface is covered by disk, the complex plane, or the Riemann sphere. So, using that one shows that being Kobayashi hyperbolic is exactly same as being classically hyperbolic. Now, this fact is obvious, and it's sort of the reason why this theory is so powerful. You get a one of the central facts become obvious once you develop the theory. Suppose X is a Kobayashi hyperbolic manifold, then the space of holomorphic mappings ODX is an equicontinuous family. This is obvious simply because we already know that holomorphic mappings are contractions. So, this is essentially saying nothing. This it trivializes one of the central facts. Now, why is this useful? Because you can use this equicontinuity and an Ascoli-Arzela type argument, which was done by Wu and Kiernan, to show that suppose you have complex manifolds X and Y and the target is complete Kobayashi hyperbolic, then the family OXY is a normal family. So, let me explain what a normal family is. In a normal family, any sequence that you consider will either have a subsequence that converges uniformly on compacts or a subsequence that diverges uniformly on compacts. So, being divergent uniformly on compacts means if I choose a compact set K in the domain, a compact set L in the target, eventually F and K will miss L. So, any compact set is moved away from any compact set in the target eventually. So, immediately combining the classical Arzela-Ascoli theorem with the equicontinuity gives this fact, and this is very useful, especially in complex dynamics. So, this is called a Montel type theorem. It was originally proved for mappings into a bounded domain by Montel. Okay. Now, as I mentioned before, the Carré theory is the smallest possible pseudo distance that you can put, and the Kobayashi is the largest. So, it is interesting to study the scenario under which both the Carré theory as well as the Kobayashi pseudo distance will coincide. When does that happen? And Lempert gave the answer in 1981 for domains in Cn. If the domain can be exhausted by domains biholomorphic to convex domains, that means you can write the domain as a union of omega n, let us say, where each omega 1 is biholomorphic to a convex domain, then the Kobayashi pseudo distance and the Carré theory pseudo distance agree. Now, this it does not matter, countably many. Okay. Now, this result is really strange in some sense, because convexity is a property that does not interact well with holomorphicity. For instance, so one really wonders why this result is actually true. Even more problematic is the fact that Lempert's proof is notoriously difficult and long. Entire theory of complex geodesics were invented to just prove this result. So, the natural question to ask is the converse true. If it so happens for a domain that the Kobayashi and the Carré theory pseudo distance agree, then is it true that the domain can be exhausted by domains biholomorphic to convex domains? So here comes the symmetrized polydisk. At the turn of the new millennium, Agler and Young, they started studying this object symmetrized bidisk.
Is it possible to give an example of a domain which is not covered by this process?
Right, not covered by. Yes, for instance, if you, the moment you take a, let's see, you want to consider a domain that is not covered. Yes, it's possible. It's possible. For instance, if you take the unit ball and remove a smaller ball, take the unit ball in Cn and remove a smaller ball, it's not, you cannot cover it by. No, it has to be an exhaustion. Sorry, it has to be an exhaustion. Exhaustion means, so let me just write that down. You should be able to write D as a union of omega n such that omega n closure is contained in interior of omega n plus 1. It has to be an exhaustion, not just a. So when you put a hole inside, right, when you put a hole inside, it's a problem. You cannot do this. So it's not just a union, it's an exhaustion. Okay. Huh? No, we are considering only domains, so open and connected sets. So points are excluded. Oh yes, yes, just a point will also work. Yes, absolutely, absolutely. So Agler and Young wanted to study the symmetrized bidisk, and the reason why they wanted to study it is they were interested in a problem that comes up in control engineering. Forgive me, I do not know the details, where they were interested in doing interpolation into the space of k cross k matrices with spectral norm less than 1. That's called the spectral unit ball. They wanted to consider holomorphic interpolation from the unit disk to the spectral unit ball, and they realized that that problem is exceedingly difficult, and they noticed that you can reduce it to interpolation to this symmetrized bidisk for the dimension 2 case. So they were interested in interpolation from the unit disk to the symmetrized bidisk, and they proved a Schwarz lemma for holomorphic mappings from the unit disk to the symmetrized bidisk. Using the works of Agler and Young, in 2004-2005, Kostara and Edigarian gave the first counterexample, and to my knowledge the only counterexample for the converse of Lempert's theorem. They showed that the symmetrized bidisk cannot be exhausted by domains, by holomorphic to convex domains, yet the Kobayashi and Caratiotti pseudo distance coincide for the symmetrized bidisk. So if this was the end of the story, I wouldn't be standing here, but just 1 year later Nikolov showed that this is something special. If n is greater than 2, then the Kobayashi and Caratiotti pseudo distance on Gn do not coincide. So this class of domains, something very unique is happening for G2 that is not happening for Gn, and it is intrinsic, I mean it is intimately tied up to that major theorem by Lempert. So once Kostara, Edigarian and Nikolov proved these results, as expected people started concentrating on the symmetrized polydisk a lot. There was a flurry of results. The most relevant to our work is the following. So whenever you want to study a domain, a common way of doing it is to write down what is this automorphism group, what is its set of proper holomorphic self maps. So here by proper I mean inverse image of a compact set is compact. So Edigarian and Zvonek got the precise structure of proper holomorphic self maps of the symmetrized polydisk. So if you have a proper holomorphic mapping from Gn to Gn, then we can find a finite Blaschke product B. A Blaschke product is nothing but a finite product of automorphisms of the unit disk, such that f composed with pi n of z1 to zn is just pi n of bz1 bzn. Okay, so what this result is essentially saying is that it can be summarized in this commutative diagram. You have the mapping from Dn to Gn, you have the self map from Gn to Gn, then you can sort of get, actually this is not an accurate picture. You have pi n here also, you have pi n here also, and you get a mapping here which is just bz1 bzn. So there is a distinguished Blaschke product that gives this proper. Yeah. Okay. So you can get a distinguished Blaschke product associated to a proper holomorphic self map of the symmetrized polydisk. In particular, you have got the entire automorphism group of the symmetrized polydisk. Those will come about when this B is nothing but an automorphism of the unit disk. This is very useful because in particular it demonstrates that the symmetrized polydisk is not homogeneous. The automorphism group of the symmetrized polydisk does not act transitively on the symmetrized polydisk. One way to see this is to just take point z1 z2 in the bidisk, look at its image in the symmetrized bidisk, that is pi n of z1 z2. If you want to map pi n of z1 z2 to 0, you have to get an automorphism of the disk that simultaneously takes both z1 and z2 to 0, which is simply impossible unless z1 is equal to z2. So this is not, the automorphism group does not act transitively, so it's not a homogeneous domain. So in 2015, Chakrabarty and Gorai extended these results not just for the symmetrized polydisk but for the symmetrized product of a arbitrary bounded domain. They considered proper holomorphic mappings from Sim D1 to Sim D2. They showed that it will arise from a single proper holomorphic mapping from D1 to D2, exactly analogous to this. So instead of pi n, you will just have pi sim on both sides, and instead of B you will have a map f from D1 to D2, proper holomorphic. So meanwhile in 2014 I studied proper holomorphic mappings between products of Riemann surfaces. So I considered compact Riemann surfaces Rj and Sj and subsets, connected subsets of Rj and Sj which are hyperbolic. So here hyperbolic means covered by unit disk or Kobayashi hyperbolic, both are equivalent because we are in dimension 1. And I considered a proper holomorphic mapping from the product of x1 to xn to the product y1 to yn. Here I assume that the mapping is finite. Finite means the inverse image of a single point is a finite set. Usually for domains this is guaranteed if both domain and codomain are equidimensional. Proper holomorphic mappings will automatically become branched coverings in that case. But here I do not exclude compact Riemann surfaces. Observe that any holomorphic mapping from a compact space to any other space is automatically proper, because inverse image of a compact set will be closed and closed subset of a compact set will be compact. So all mappings will become proper. To exclude trivialities, I needed to put the condition of finiteness. So once you put the condition of finiteness, the conclusion is that the mapping will split. You will get mappings from the Fi will map to, I'm a bit confused. Each Fi will be actually a function of only one of the factors and mapping into Yi. Okay, so essentially the mapping splits. Now let me briefly describe the central idea of the proof of the result in the previous slide as well as the proofs of the results of Edigarian Zvonek and Chakrabarty Gorai. All of them rely on a technique introduced by Remmert and Stein in the 60s. They were the first to systematically analyze proper holomorphic mappings between products. I will just illustrate the idea for the bidisk. Suppose you have a proper holomorphic self map of the bidisk F1 F2. You fix a point on the disk the boundary of the disk, the circle, the unit circle. Fix a point W0 on the unit circle and choose a sequence Wn from the unit disk converging to W0. So essentially the picture is as follows. You just choose a sequence converging to W0. Then you consider the mappings Hn to be just f of z comma Wn. Okay. Now the normality of this sequence follows because the codomain is bounded. We have a Montel's theorem. So this will be a normal sequence. That means any sequence, this sequence will either have a convergent subsequence or it will diverge uniformly on compacts. More generally, all the results of this type will always have the target being complete Kobayashi hyperbolic. The moment the target is complete Kobayashi hyperbolic, we have at hand a version of Montel's theorem that will show that the family of holomorphic mappings into this space is automatically normal. Now, because of properness, any subsequential limit h of the sequence Hn must map into the boundary of the polydisk, the bidisk. Properness is equivalent in the case of domains to the condition that for any sequence converging to the boundary in the domain, no subsequence of the image converges to an interior point. So the properness forces the map to go into the boundary of D2. Now one can argue and show that one of the components of H must in fact be constant when this happens. Now in general what we do is we consider all possible points on the boundary and look at all possible subsequences, all possible sequences that converge to the boundary and analyze all possible subsequential limits. This analysis will depend on the setting we are in. Depending on the setting we are in, we will have to set up a particular differential equation and do an analysis, and that using that analysis one can conclude that each component of the original function f depends on only one of the factors. This technique also works in the case of the symmetric product of a bounded planar domain. Simply by precomposing with pi n, you have a mapping from the image of you have a mapping from, let's say, symmetrized polydisk to symmetrized polydisk. You can convert it to a map from the polydisk to the symmetrized polydisk simply by composing with pi n and then doing a similar analysis. Now the Riemann-Stein technique absolutely does not work when some of the factors are compact or compact with finitely many punctures. So in the result that I have, I did not exclude such factors. I allowed all compact Riemann surfaces that are hyperbolic also. So to deal with those factors, I relied on a result of Imayoshi that states that for these factors there are only finitely many holomorphic mappings that are non-constant in the first place. So a result of Imayoshi says that if you have a compact hyperbolic Riemann surface or a compact hyperbolic Riemann surface with finitely many punctures, then the collection of holomorphic mappings between two such surfaces is automatically finite, the non-constant ones of course. So in 2001, Divakaran and I extended Imayoshi's result to a wide class of complex manifolds. I am not stating the result here because the statement is a bit long and technical. At the same time, we gave a proof that highlights the role of hyperbolicity. Imayoshi's proof uses mainly techniques from the theory of Fuchsian groups. So any compact hyperbolic Riemann surface will be just the unit disk quotiented by a Fuchsian group, and in case it's just a compact Riemann surface or with finitely many punctures, that Fuchsian group will have some nice properties. He uses those properties to prove this result. We bypass certain ideas in his proof by relying on hyperbolicity. Okay. Now this is a result that was jointly obtained with Barali, Biswas, Divakaran, where we wanted to see whether the structure theorem for proper holomorphic mappings that I have for Riemann surfaces is also true when the target is a symmetric product and not just a product of Riemann surfaces. So the result runs as follows. I have a product of Riemann surfaces which are non-compact obtained by excising a non-empty indiscrete set from a compact Riemann surface. So I start with a compact Riemann surface and remove a set, and that set should be large. That's quantified by saying the set is indiscrete. The target will be the symmetric product of a Riemann surface Y, which will be a bordered with C2 smooth boundary. That means I start with a compact Riemann surface and punch out finitely many disks, such that, finitely many smooth disks, I remove them. Suppose you have a proper holomorphic mapping from X to sim n Y. Then again the mapping splits. I can find proper holomorphic mappings Fj from Xj to Y such that f of x1 to xn is just pi sim composed with f1 x1 comma dot 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 fn xn. Again the mapping split. So you might ask, what's the big deal? Isn't just a mutation of the ideas used by Edgarian and Zvonek for the symmetrized polydisk combined with whatever techniques I use for the products of Riemann surfaces, doesn't that work? Doesn't just directly just give this result. This is not the case. There are two primary obstacles to directly using that, directly just mutating the earlier ideas. The first obstacle is that it is not true that the symmetric product of a Kobayashi hyperbolic Riemann surface is Kobayashi hyperbolic. Recall that I had mentioned for the Riemann-Stein technique to work, you always need the target to be complete Kobayashi hyperbolic so that you can start the argument, you can use a normal family's argument. But if you just start with a Kobayashi hyperbolic Riemann surface, there is no guarantee that the symmetric product is Kobayashi hyperbolic. In particular, if you look at the twofold symmetric product of C minus 0, 1, it turns out that it's biholomorphic to C2, where the Kobayashi pseudo distance is identically 0. The second obstacle is that to apply the Riemann-Stein technique on the target, if it's a manifold and not a domain, we need some special charts. This was available for the product of a Riemann surface, but no, it's not apparent that such charts exist when you take the symmetric product. So I'll just briefly explain how we overcame the obstacles. The first one is fairly straightforward. We just identified a natural class of Riemann surfaces for which it is true that the symmetric product is hyperbolic. So if X is a connected bordered Riemann surface with C2 smooth boundary, then the symmetric product is Kobayashi complete. So for the proof, we constructed some special peaking functions on a bordered Riemann surface using the del bar method, and this itself seems to be new, and I think that this result itself is of independent interest. Now for the second problem, the lack of special charts, there is no such problem if everything was happening in a domain in Cn. So what we did was we translated the entire problem to a domain in Cn by using a classical theorem of Behnke and Stein. The theorem of Behnke and Stein says that on any non-compact Riemann surface, the space of holomorphic function separates points of X. That means given any pair of points x comma y on a non-compact Riemann surface, I can find a holomorphic function such that f of x is not equal to f of y. So in particular, using the Behnke-Stein theorem, you can construct a non-constant bounded holomorphic function chi defined on some open connected set that contains y closure. So this y, was a bordered Riemann surface with C2 smooth boundary. There is an ambient Riemann surface from which y is produced. So the closure is taken in that ambient Riemann surface. So this is a brief summary as a commutative diagram that summarizes the proof, how I am able to take the mapping all the way to Cn. So I will not go into the details, but this single diagram summarizes the ideas used in the proof. So now let me come to the second result on the symmetric product. It's a Schwarz lemma. So as I told, the original study of the symmetrized bidisk came from the work of Agler and Young, who proved a Schwarz lemma for the symmetrized bidisk. Around the same time, there was another Schwarz lemma for the symmetrized polydisk produced by Nochrane and Ransford. Nochrane and Ransford viewed the mappings into symmetrized polydisk as an algebraic multifunction. An algebraic multifunction is just an assignment of a finite set of points to each point in the unit disk, such that this finite set of points satisfy an polynomial equation whose coefficients are holomorphic functions. So they viewed mappings into the symmetrized polydisk as algebraic multifunctions. Both the results of Nochrane and Ransford as well as that of Agler and Young use a fair bit of operator theory. In particular, Nochrane and Ransford used a theorem from Banach algebras proved by Santini. The result of Nochrane and Ransford was extended to the symmetric product of a bounded domain by Vikramjit Chandel in 2017. His techniques are very similar to the original techniques used by Nochrane and Ransford. Now here is the Schwarz lemma I have proved recently for mappings into the symmetric product of a Riemann surface. Let X be a Riemann surface and F from the unit disk to sim n X be holomorphic. Here let me just set up the notation. H is the Hausdorff distance between sets induced by the pseudo distance on the subscript. So the left hand side here is the nth power of the Hausdorff distance introduced by the Mobius distance on X. Now there is an abuse of notation happening here. Pi sim inverse Fx and pi sim inverse Fx naught are points in the Cartesian product Xn, right? They are not subsets of X. So what I am doing is, since I know what pi sim does, any two points which are there in the inverse image will just differ by a permutation. So what I am going to do is I am going to forget that it is lying in Xn and just view it as a subset of X. So I look at pi sim inverse Fx and pi sim inverse Fx naught, look at it as subsets of X and take the Hausdorff distance power n with respect to the Mobius pseudo distance. This will be less than or equal to the Mobius pseudo distance of X and X naught. So this is the Schwarz lemma I have for the symmetric product of a Riemann surface. Question is this just another pointless generalization? Why do this extra effort? Answer is a big no. Let me try to explain the motivation for trying to prove this result. First is that obviously it's a generalization, it subsumes the earlier work of Nochrane, Ransford and Chandel. However, our proof is fully function theoretic and almost entirely elementary. We use no operator theory. The maximum tool we use is basic properties of a function called the pluricomplex Green's function. Our proof is fully function theoretic, does not use any tools from operator theory. The second point is what is more interesting. It is easy, it's a nice puzzle to show that for a domain in C, either the Cartesian pseudo distance is identically 0 or it's a distance. It cannot happen that the Cartesian pseudo distance is 0 for some xy x not equal to y and not 0 for some other zw. That cannot happen. Either it's identically 0 or it's a proper distance. But for Riemann surfaces this is not true. There are Riemann surfaces for which the Cartesian pseudo distance and the Mobius pseudo distance, for some pair of points it's 0 and for other pair of points it's not 0. Our result is true for all Riemann surfaces, irrespective of whether it's hyperbolic or partially hyperbolic like this, or the metric is identically 0. Of course, if the Mobius distance is identically 0, the left hand side is also identically 0. So the result is sort of trivial for all compact Riemann surfaces. However, for non-compact Riemann surfaces this result is not trivial. In addition, the same techniques that we use in the proof we have used to show several other Schwarz lemmas. In particular, we show a Schwarz lemma for quasi-balanced domains, and not only that, the result of Santini that was used in earlier papers, we give a simple straightforward elementary proof using our techniques. So these are the reasons why I feel this is not just a pointless generalization. So the main tool that I use so that I can bypass the use of Santini's theorem and earlier techniques is it an extremal function. So let me just define the extremal function for you. on a complex manifold, fix a point z0 and look at the collection Px z0 and take the supremum. The collection Px z0 is the collection of all functions phi on x that satisfy the following 5 conditions. Phi is upper semi-continuous, 0 less than or equal to phi less than 1, log phi is plurisubharmonic on x, phi z0 is 0. For any coordinate system around the point z0 that takes z0 to the origin, the quantity phi of x by mod zx is bounded above in a neighborhood of z0. So you take the supremum over all this collection. One might wonder how this was constructed. The log of this lambda x, is known in the literature as the pluricomplex Green's function. If you specialize to dimension 1 and just look at domains in C, you can easily see that this log lambda x is nothing but the usual Green's function on a domain. So this construction generalizes the construction of the Green's function in the domain. However, there is one critical problem: this function is not symmetric, whereas the Green's function for bounded domains is symmetric. This pluricomplex Green's function has been used in the literature to prove several deep facts. In fact, the theorem of Lempert that I stated several slides ago also uses the log of this function. Let me just describe the basic properties of this function. If you take a bounded domain, then mod z minus z0 is clearly there in that collection PD z0. All the properties are trivially satisfied. So lambda d z z0 is always greater than 0 for all bounded domains. Second is that even this pluricomplex Green's function or the extremal Green's function also has a distance decreasing property. Suppose you have complex manifolds x and y and a holomorphic mapping f from x to y, then lambda y fx fz0 is less than or equal to lambda x z0. So in some sense holomorphic mappings are distance decreasing, even though this is not a distance. And the extremal function for the disk coincides with the Mobius distance. Now let me just briefly outline the proof. The essential idea is to use the distance decreasing property. The way I do it is, on the left hand side of what I want to prove is a really complicated object involving the Hausdorff distance. What I do is I create an intermediate object, this function h1. This function h1 has been so cooked up to dominate the Hausdorff distance and at the same time satisfy all the conditions to put it in this collection Px z0. So I define this function h1 in this way. Then we have that away from the critical set of the map pi sim, this function h1 is there in P sim n x of z0. So this is a function that is there in that collection of functions whose supremum is nothing but lambda x z z0. So I construct this function and show that it is there in that collection. Now because of that, it is immediate that h1 of z is less than or equal to lambda sim n x z z0, just by the fact that it is there in that collection. Now one uses the distance decreasing property to show that lambda sim n x fx fx0 is less than or equal to lambda d xx0. And we already know that lambda d xx0 is nothing but m d xx0, the Mobius distance. So consequently what we have shown is that h1 fx is less than or equal to m d xx0. But the problem is all this is valid provided this z0 is not there in the critical set of critical values of this map. What happens if it's there in the critical values? We have to do an analysis. So I have not mentioned how that is done. Essentially what you do is, if it so happens that the mapping f is so peculiar that it maps entirely into the critical set V, then we can convert it to a mapping to a lower dimensional symmetric product. If it so happens that the image of f itself is contained in the critical set of the map pi sim, then you just transfer it to a lower dimensional symmetric product. Now the proof is complete, as the left hand side in our theorem is dominated by H1, and we are done. So finally let me just say what simplifications are possible by the use of this technique. This is the first result in the literature that I know of that uses the pluricomplex Green's function to obtain Schwarz type lemmas. The same technique can be used to give simple proofs of Schwarz lemmas for quasi-balanced domains. These are domains that have a twisted circle action on there's a twisted circle sitting in the automorphism group, as well as Schwarz lemma for the spectral unit ball. So several earlier results you can give really short proofs using the same technique. Not only that, the result of Santini that is usually used in the literature to prove Schwarz type lemmas can be obtained easily using our technique. So let me just finish by stating Santini's theorem. Suppose you have the space of n cross n complex matrices. Let rho denote the spectral radius. Then for any mapping from the unit disk to the space of matrices, rho composed with f is subharmonic. This follows directly from our techniques. So thank you for I hope I am not exceeding.
Any questions? I have one question.
Sure.
Suppose you take a just compact Riemann surface genus G.
Huh.
What is Symmetrization of G? Is there some description?
It's a compact manifold fold. I believe so, but I have not explored that part of it. I think
genus 0 it is just a projective space.
right.
For the higher genus,
It is studied, but I have not explored that much. There are some description, especially of homology groups and all that. It is studied.
but
Sim 2 of
say genus 2 curve.
genus 2 curve. What will it look like? Sim.
Fine, perhaps this is not of interest to you because you are only looking at non-compact.
Mainly, I am dealing mainly with the non-compact case,
Perhaps
but
not even geometrically finite, so it's
right.
or removed from your interest, but it should have some nice description.
Right. Probably there is.
So also when you define that mx, there mx, right?
Huh.
So you use upper half, you use unit disk.
Correct.
Yeah, I mean, what is the problem? Only if I use the upper half plane,
Huh.
disk,
Huh.
only the norm is going to give you the problem?
So one advantage of using the unit disk is as follows. So if you notice in the definition of the Carathéory pseudodistance, why is it not infinite? For instance, why is it not infinite? The reason is I have normalized it so that when I am taking the supreme and the second coordinate always goes to 0. So what happens is, say there is a sequence such that supremum rho d f of w 0 goes to infinity. That cannot happen because this sequence will either have a convergent subsequence or a compactly divergent subsequence, but it cannot have a compactly divergent subsequence because f of z is always 0. So because of that, it's easy to show now that the Carathéory pseudodistance at any for a pair of points can never be infinity. So because you have access, because the unit disk is bounded, essentially the same thing will work for upper half plane also. That is also complete when you put the equivalent of the Poincare distance, but it's just more convenient to work with the unit disk. That's all.